Regression model in machine learning is like a tool that helps us understand the relationship between one or more input variables and an output variable. The goal is to predict the value of output variable based on input variables. Some of the famous applications are predicting house prices and forecasting sales, etc. Now, simple linear regression is a foundational statistical method and the most basic form of regression. It's used when we have one input variable and one output variable, and if relationship between them is linear, simple linear regression is particularly effective at making correct predictions. For example, predicting exam scores. We can predict student scores based on number of hours they study. The relationship between scores and hours of study is linear, assuming student scores increases if they study more. And customer satisfaction prediction. We can predict customer satisfaction scores based on the waiting time, since longer wait time leads to lower satisfaction scores, suggesting a linear relationship between them, and many more examples like this. Now let's see how simple linear regression works in detail. Okay, let's start with a simple problem. Let's say there are some fixed number of people and these people are making some objects, and there is a data of how much time it took them to make some number of objects. Let's say the number of objects are represented on x-axis and the time it took them are represented on y-axis. Now the relationship between these two are clearly linear because the more the number of objects, the more time it will take to make them, and the data is represented in graph like this. For example, let's take this data point and let's say it represents a two number of objects and the time it took them will be, let's say, 2.2 units of time. And if you want to predict how much time it will take to make some m number of objects, all we gotta do is to draw a line that best fit these data points, and after drawing this line from this point m, draw a line parallel to y-axis to this best fit line, and then from here draw a line parallel to x-axis, and we'll get our prediction time t. What is a best fit line here? A best fit line is a line which has the minimum error value, and the error here is measured using mean squared error, which is nothing but the average of the square of the distance between all the actual values and the predicted values. So let's say we have n number of objects, and let's say yi is the actual value for the ith object, and y pred of I is our prediction for the ith object. The mean squared error function will look something like this. For example, let's take this two number of object. The actual time it took is 2.2 units of time, and if we are making prediction for these two number of object, we will be predicting something like, let's say, 2.4 units of time. Now the error here is calculated using the square of distance between these 2 points. Since the x value is same here, the error becomes y minus y pred the whole square. Now if we do this to all these points and then take the average, we will get the mean squared error. Now I'm gonna write this error function simply as e for convenience, and this error function is considered to be the optimal way of calculating the error in simple linear regression, which is 1 by n into sigma equal to 1 to n by I minus y pred of I whole square. Now how to find this best fit line? Should we draw some random lines in this 2D plane and then take the one with the less error value? Well, there are infinite such possible lines to draw, and how to find the one with the minimum mean squared error value? Well, we can do that using an algorithm called gradient descent. Let's understand how it works in detail. Let's start with the simple line equation y equal to mx plus c, where m is the slope of the line and c is the intercept. Now I'm gonna rename this m and c as capital W and b, so it becomes y equal to capital W into x plus p. Now the idea is simple here. This best fit line will also have some value of w and b. Now to draw this best fit line, all we gotta do is find this w and b value and we are good to go. Now to do that, we will start with the value of w and b. Now generally everyone starts with the w and b value as 0, because when w equal to 0 and b equal to 0, the equation becomes y equal to 0, which is the equation of x-axis, and it will be easier to move from x-axis to the best fit line no matter where the best fit line is. And note that initializing the w and b value with a random value also works just fine. Let's say for this x-axis, the value of w and b are w1 and b1. So we start with this x-axis, and this x-axis will have some error value with these data points, and let's say the error is e1. Now we will update this w1 and b1 to a new value of w2 and b2 in a way that the error e1 is reduced. Let's say the error is reduced to e2. Now by doing that, the line will move closer to the best fit line, let's say something like this. Now again in next iteration, we will update this w2 and b2 to a new value of w3 and b3 in a way that this error E2 is again reduced to, let's say, E3. Now again the line will move closer to the best fit line, something like this. Now we will repeat this process for several iterations until we reach this best fit line. Now this is what gradient descent algorithm does. It minimizes the error function by iteratively updating the parameters which are W and B in this case. Now the formula to update these parameters W and B are as follow. The formula to update W is W equal to W minus alpha into dou E by dou W, and the formula to update B is B equal to B minus alpha into dou E by dou B. Here alpha is the hyperparameter called learning rate, and dou E by dou W is the partial derivative of the error function with respect to parameter W, and dou E by dou B is the partial derivative of the error function with respect to parameter B. Now how in the world does updating the parameters using this formula helps in reducing this error? Let's understand it using some graphs. Now the equation of error function is E equal to 1 by n into summation of y equal to 1 to n yi minus y pred of y whole square. Now here y pred of y is obtained by substituting the xi values in the line equation. So y pred of y becomes w into xi plus p. Now if we consider the error equation as a function of w and p, the equation looks like this. Now in this there are two variables w and p. Now for now let's assume that w is the only variable and the remaining all including b are constant, and if we write this error equation as a function of only w, it looks like this, and this is a quadratic equation of form y equal to ax square plus bx plus c. So this error function will have a parabolic curve. Now let's draw graph for this error function. Let me also write the formula to update the w value, which is w equal to w minus alpha into dou E by dou W. Now if we take the w value on the x-axis and the error value on the y-axis, the graph will look like this. Now let's say our w value is somewhere around here on the x-axis. Now for this value of w, let's say the value of error is this one. Now from the graph it is clear that the error value is minimum at this single point, and this point is called the global minima. Now our goal is to reduce this error value, and to do that we need to move this point towards the global minima. So we need to move towards the right, and to do that we need to add some value to this w so that it moves to the right. Error value will be reduced and this point will reach the global minima. Let's say if our w value is somewhere around here on the x-axis and we are at this point in the curve. Now in this case we need to move towards left to reach the global minima, and to do that we need to subtract some value from this w value. Now how do we know when to move towards the right and when to move towards the left? And to know that we calculate the partial derivative. For those of you who don't know what partial derivative does, it calculates the rate of change of the error function with respect to this variable w while keeping all other variables constant. In simple words, it gives the slope of a curve at a given point. So if we calculate the dou E by dou W value at this point, it gives the slope of the curve at this point. Now the slope here is a negative slope, which means dou E by dou W value will be negative, and negative into negative becomes positive, and we will end up adding some value to the W. So the point moves towards the right, error value will be reduced, and this point will move towards the global minima. And let's say if we are here and we calculate the dou E by dou W value here. Now here the slope is a positive slope. Since slope is positive, dou E by dou W value will be positive, and we will end up subtracting some value from this W. So W moves towards the left, this point moves towards the global minima. Now we know when to move towards the right and when to move towards the left. Now what is this learning rate doing in this equation? Now this learning rate helps in controlling the movement of this point to reach the global minima in an optimal way. Let's say learning rate is not included in the equation. So the equation becomes W equal to W minus dou E by dou W. Now in general dou E by dou W will be a large value compared to this W value. So if we are at this point and we calculate the dou E by dou W value at this point, and learning rate is not included in the equation, we will certainly know that we need to move towards the right. But since dou E by dou W value is large, we will end up adding a very large value to the W. So it does move towards the right, reaches the global minima, and it doesn't stop there. It overshoots and goes beyond this global minima point, and let's say it reaches somewhere around here. Now again we calculate the dou E by dou W value at this point. Now here we will get a positive slope and we know that we will move towards the left. And again we know that we need to move towards the left, but since dou E by dou W value will be again large, in fact even larger than the previous dou E by dou W value, it again goes towards the global minima, overshoots, and now it will reach somewhere around here. Like this, the point will keep on oscillating, never reaching the global minimum point. That's why the learning rate is multiplied with the dou E by dou W value here. In general, a very small number is chosen as a learning rate, like 0.001 or 0.0001. Now with this learning rate, let's say we are here, and like always, we calculate the dou E by dou W value, and this time we multiply the dou E by dou W value with the learning rate, so that the value added to the W is not too large, and this time it won't overshoot and ends up somewhere near this global minima. Let's say the point moves towards the global minima and it reaches somewhere around here. So the point moved from here to here in the first iteration. Now again we calculate the dou E by dou W value here. The dou E by dou W value will be somewhat small in this case since the slope value is small here, and again we multiply it even small value alpha and won't overshoot and it will end up much closer to the global minima. Let's say it reaches a point around here. So in second iteration the point moved from this point to this point. Like this, after several iterations, the point will eventually find its way to the global minima. Now, I did all this by only considering the value W, but there is also value B in the error equation. Now, here the W is taken on x-axis, E is taken on y-axis, and if we also consider the value of B on z-axis, the graph will look something like this one. It will have a bowl shape with one global minimum point, and of course the E value will be dependent on both the W and B value, and both the W and B value are adjusted in each iteration in a way that the error is reduced. This is a random image from internet where the path of the point in each iteration is shown, which is moving towards the global minimum. Now we know for sure that updating the values of W and B using these formulas for sure reduces the error value, and in each iteration the error value will be reduced. Our line will move closer to the best fit line and takes the position of the best fit line. What is the dou E by dou W value and dou E by dou B value here? For that we just need to do the partial derivative on error function. We know the equation of error function E equal to 1 by n into summation of I equal to 1 to n y I minus w into xi plus b whole square. We need to partially derive it with the w. I took the partial derivative inside the summation, so the equation looks like this. And after performing the partial derivative on this part, the equation looks like this: 1 by n into summation of I equal to 1 to n 2 into yi minus w into xi plus b. Now this w into xi plus b is nothing but the y pred of I, and partial derivative of this one is minus xi, and I took the minus value and 2 value outside the summation, so the equation becomes minus 2 by n into summation of I equal to 1 to n yi minus y pred of I into xi, and I renamed dou I by dou w as dw so that it is easier to code. Similarly, I have done the partial derivative of the error function with respect to p, and here this partial derivative value becomes minus 1, and the equation looks like this: minus 2 by n into summation of I equal to 1 to n by I minus y pred of I, and I renamed it as db. Now let's put it all together to create a simple linear regression model. So we initialize w and b with the 0, so we start with the x-axis and then do this process for several number of iterations. Here the number of iterations is also a hyperparameter. We need to experiment with the different values and choose the one that best suits our training data. So in each iteration we calculate the y pred value, and using this we calculate the dw value, and then we calculate the db value, and then we update this w and b using this formula. And after each iteration our initial line will move closer and closer towards this best fit line, and after all iterations are completed our line will take the position of the best fit line. Now let's see how it's implemented in Python. Okay, let's start with importing the numpy and pyplot libraries. Now I'm going to create my own dataset for the example I have explained, and I'm going for a very small dataset to understand everything clearly. So I'm going to initialize two empty list capital X and Y, and I'm going to populate them as follows. Let's go for just 25 objects in the dataset. So for I in the range of 1 to 26, this will give me numbers from 1 to 25, and first I'm going to create a random number. So np dot random dot uniform of 0 to 2. This np.random.uniform will give me a random number between 0 and 2, and I'm going to append the value of I to the x, and I'm going to append the value of I plus random number to the y to give some randomness to the data. Now let's print some data to see how our data set looks like. Okay, this is how the data looks like. So to make 5 objects it's taking 6.35 units of time, and to make 15 objects it's taking 16.58 units of time, and to make 25 objects it's taking 25.21 units of time. So the data looks good. Now I'm going to convert this x and y list into a numpy array. Okay, now this np.array of x will convert this list x into a numpy array, and then I reshaped them into a two-dimensional array. Let's see how x and y looks like. So this is how x looks and this is how y looks. It's good. Let's also print their shapes. So x is a two-dimensional array with 25 elements in them, and y is also a two-dimensional array with 25 elements in them. Now let's split this data into test set and training set. Let's go for 20 objects in the training set and 5 objects in the test set. So I have taken first 20 objects into the training set and then the remaining into the test set. Let's also print their shapes to see how they looks like. Okay, we got our two-dimensional arrays with 20 elements in the training set and then remaining 5 elements in the test set. Now let's also visualize these points in a 2D graph. So this is how the training data looks in the graph. The number of objects are represented on x-axis and the time it took them are represented on y-axis. Now we have to draw the best fit line that best fits these data points. Let's also visualize the line to see how it looks like. We are going to start with the x-axis, so let's just include that, and remember that we are initializing the w and b value with 0, so I'm going to say 0 into x train plus 0. This is nothing but the equation of line y equal to mx plus c, and instead of m and c we took w and b, and we are going to initialize them with 0, so the line equal to 0 into x train plus 0. Let's also include that here. So this is how the line looks like that we are going to start with. Now we are going to move this line to the best fit lines position. Now we got the data and everything ready. Let's start building the model. Let's build the model now. I'm going to name the model as SLR, standing for simple linear regression, and there's going to be two methods in it, fit and predict. Let's start with the init function. Now there is two hyperparameters in this, which are learning rate and the number of iterations, and I'm going to give a default value of 0.001 to the learning rate and a default value of, let's say, 1000 to the number of iteration, and let's initialize everything. Self.learning rate equal to learning rate, and then self.number of iterations equal to number of iterations. Also I'm going to initialize the w and b value 0 in this init function, so self.w equal to 0 and then self.b equal to 0. Now let's go for the fit function. To fit the training data we need x train and y train, so x train and y train, and first we need to find how many data are there in the training set. To do that we can just say n equal to x train dot shape of 0. Now the x train dot shape will give a tuple of 20, 1, and to access the first element in it we need to say x train dot shape of 0. So we will know how many elements are in the training data, and then we know the drill now. So we need to repeat the process for the number of iteration times, and in each iteration we need to first calculate the ypred value, dw value, db value, and then update the w and b value. So let's just do that. So for I in range of self dot number of iterations, first we need to calculate the ypred value. So ypred equal to get ypred, so we just need to substitute the xtrain values in the line equation, which is self dot w into xtrain plus self dot b. For current value of w and current value of b, we will get some predictions. Now let's calculate the dw value and db value. We know the formula for both of them. For dw it's 2 by n into sigma equal to 1 to n yi minus ypred of I into xi, and for db it's minus 2 by n into sigma equal to 1 to n yi minus ypred of I. So dw equal to minus 2 divided by n into np dot sum of y prime minus ypred into xtrain, and then dd equal to minus 2 divided by n into np dot sum of right. So dw equal to minus 2 divided by n into np dot sum of yi minus ypred. Here yi is ytrain, here xi is the xtrain. So this is how we calculate dw, and this is how we calculate db. Now we just need to update the value of w and b. We know the formula to update them, which is w equal to w minus learning rate into dw, and b equal to b minus learning rate into db. So self dot w equal to self dot w minus self dot learning rate into dw, and to update db, self dot db equal to self dot e minus self dot learning rate into db. Okay, good. We are updating the w and b value on each iteration, and after all the iterations are completed, we will reach the best fit line. Now let's also initialize where our line is in each iteration. So to do that, I'm going to first create the line equation. So line equal to self dot w into xtrain plus self dot b. Now let's also print the error value at each iteration. So error equal to, we also know the formula for the error, which is 1 by n into summation of I equal to 1 to n yi minus w into xi plus b whole square. So it is going to be 1 divided by n into np dot sum of y prime minus line whole square. Now for those of you who don't know these numpy operations, I have created some small examples here. So I have created 3 numpy arrays with x having 1 to 3 elements in them, y having 4, 5, 6, and z having 2 to 2. So if we multiply a scalar value of, let's say, 2 with this numpy array x, this 2 will be multiplied to each and every element of this array, which is called broadcasting in Python. So 2 will be multiplied to every element. So 1 into 2 is 2, 2 into 2 is 4, and 3 into 2 is 6, and we will get to 2, 4, 6. And if we are subtracting 2 numpy arrays, it does say element wise subtraction, means it will calculate 2 minus 4, 4 minus 5, and 6 minus 6, which gives us minus 2, minus 1, and 0. And if you are multiplying another numpy array to if you are multiplying a numpy array to another numpy array, it does element wise multiplication. Here we are multiplying this array with z, so 2 will be multiplied with minus 2, and another 2 will be multiplied with minus 1, and then this 2 will be multiplied with 0, and we'll get minus 4, minus 2, and 0. And if we are making square of a numpy array, each element in the numpy array will be squared. So the square value is 16, 4, 4, 16, minus 1 minus 4 is 16, minus 2 minus 2 is 4, we'll get this. And if you are doing np.sum, it will give a scalar value of the sum of all the elements of numpy array. So sum of all this is 20. Now that's the numpy operations. So this dw, db, and e are exactly these formulas. Okay, now let's also print the error and visualize the line. So print, let's say, value of e, and then let's visualize the line. Now let's also write function for the prediction. So def, I'm gonna call it predict, and to do prediction we just need the value of x. Just need to substitute this x values in the line equation. So x equal to self.w into x plus self.p, and I'm going to run it. Now let's create the object for the model. I'm gonna call it as a SLR model equal to, it's going to be SLR, and I'm going for 0.001 as learning rate, and I'm starting with 100 number of iterations. So this will create our model, and then let's fit our training data into it. So SLR model dot fit trying for the right one. Now you see here we are starting with this x-axis line. This is our initial position, and after the iteration 1 the error value is this one, and our line has moved somewhat closer to the best fit position. And in next iteration the error is reduced from 85 to 43, and then our line moved a little bit closer to the best fit line. And in next iteration the error value is reduced from 43 to 22, and the line moved further towards the best fit position. Like this, after the 100 iterations, our error has reduced from 80 something to 0.699. So there is more. Yeah, our error has reduced from 80 something to 0.697, and our line has moved to its best fit position. Let's play around with this learning rate. Let's say I choose a learning rate, a higher value, let's say 0.01. Now let's see what happens now. Now here you see that the error is 593 in the first iteration, and after second iteration it's jumped to 2106. So the error is increased, and in third iteration it jumped to 7487. You can see that the error is increasing and the line is moving further away from the best fit position. This is what I have explained before. So if the dou by dou w value is large and we are not multiplying with a smaller number of learning rate, the point will overshoot and it will keep on oscillating and it won't reach the global minima. In fact, the line will move further away from its best fit position. A learning rate of 0.01 looks good for this example, and for 100 iteration I believe we got a minimum error of 0.697. I am going for 1000 iterations. Let's see if the error value is reduced or not. Okay, after 1000 iterations our error has reduced to 0.59. Even if we increase the number of iterations, now there won't be a much reduction in the error, so we can say that the line has reached its best fit position. So we have started with this line and slowly moved our line to its best fit position. Now let's do some predictions and see how this model works on the test dataset. And I'm also going to compare this model with the SKLens model. So first I'm going to create the SKLens model. This code will import the linear regression from the SKLens linear model, and I have fitted my dataset into this SKLens model. So the both models are ready now. Let's compare both of them on the test dataset. So to make the prediction, we just have to pass the test dataset into the predict method like this. Now I have made the predictions for both this SLR model and this SKLens model and stored them in these two variables. Now let's compare it to the real timings. Now I have put everything in this column stack method, which prints them in a table like this. Now the number of objects are 21, 22, 23, 24 and 25. So the actual time it took to make 21 objects is 21.18 units of time. Our SLR model has predicted it as 22.34 units of time. The SKLN model has predicted it as 21.91 unit of time. Let's say we have any best values. Let's say for 24 objects actual time it took is 25.24 unit of time. Our SLR model has predicted it at 25.45 unit of time. The SKLN model has predicted it as 24.85 unit of time. So our model is performing good. Now it is not as good as the model in the SKLN. It is better optimized, but it works just fine. Now a very important thing to note here is that I haven't scaled my data, because already my data are pretty much in the same scale. Means the data in the X and data in the Y are pretty much in the same scale. But if you are using a different data and your data is not scaled, please bring the X and Y values to the same scale. Otherwise the best fit line won't be reached. And that's it. This is how simple linear regression works. Please feel free to correct me if I have missed anything or explained anything incorrectly at any point in the video.